Hello, I'm Kelsey Wimberly, and I'm going to show you the projects I made in Unity for my math class on curves and surfaces at DigiPen Institute of Technology. The first project was the Casteljau algorithm for polynomial functions. This project illustrates how the coefficient of Bernstein polynomials affects the shape of a polynomial graph. This is done with a graph with d+1 number of points that are evenly spread out from 0 to 1 on the x-axis. The equation to get the y-value curve is the sum of each point's y position times the Bernstein polynomial of degree d. The default curve is y equals 1, since each Bernstein polynomial sums up to 1, but moving the points around stretches the curve. I also implemented a second method to calculate the curve with nested linear interpolation. For each x value on the curve, a table is recursed through with the equation 1 minus t times 0.1 plus t times 0.2 for all points, and these values continue to be recursed through d times until a single value is left. This produces a near identical result to the Bernstein curve equation. The second project was the Casteljau algorithm for Bezier curves. This project demonstrates the creation of a smooth curve from placed points. Unlike the previous project where the x values are known and only go from 1 to 0, this project now uses both the x and y coordinates of the placed points to determine both coordinates of each part of the curve. Bernstein basis form is calculated the same way as before, but now we track the x values as well. Another method, midpoint subdivision, was similar to NLI, but the curve becomes more accurate the more times the algorithm is recursed through. NLI changes, though, to now show shells that indicate how each point on the curve is found. The NLI algorithm makes use of a t-value that determines where in between each connecting point the subdivision lies. For example, a t-value of 0.5 shows the midpoint of each subdivision. Like the previous project, these three methods generate very similar curves. The third project was interpolating polynomials. This project produces a parametric polynomial curve passing through the placed points. Unlike the previous projects, this one only has one method. This algorithm creates a divided difference table from the points placed in the scene and creates the curve's equation using the Newton form. I also enhanced this project by making it 3D, allowing for dynamic viewing of the curve with the added z-axis. I made placing points easy in this 3D space by using sliders and a visible sphere to show where the point will be placed. These are the projects I made for my math class in my graduate degree. Thank you for watching.